Hello, everyone. So my name is William Yu. I'm an LTCC component designer with Mini Circuits. So today I'm here to present some of the innovations we've made with regards to LTCC filter design, specifically in the realm of high rejection filtering. So to start off, I need to introduce our BFHK-series of ultra high rejection filters. So this might sound like a bit of a sales pitch at the start of this presentation. So this technology platform was released roughly 2 to 3 years ago in 2022. Currently has 18 filters covering the bands between 4 and 36 gigahertz. And in the future, we do hope to expand this to low-pass filters and high-pass filters. So everything discussed here is actually covered in US patent numbers. So if you care about the nitty-gritty details of the design, that's available for you to view. Apologize for people that are deeply curious. In this presentation, I'll only be going over sort of high-level details. So what are the key features of this BFHK line? So typical mid-band insertion losses of around 2.5 dB, not super remarkable. Percentage bandwidths between 20 and 30%. Once again, this is rather typical of many of our filters. But the key feature being, the absolute key feature of this series being the 80 dB typical stop band rejection. And this rejection bandwidth extends a little bit past 1 octave, so quite wide with regards to other filters of a similar topology. And another huge feature of this BFHK series is that for the performance, the cost and size is relatively small compared to alternatives. So case sizes range between 1008 and 1812, and that is 2.5 by 2 millimeters and 4.5 by 3.2 millimeters. So this series came out of a need we saw in test and measurement specifically. But in the past few years, we've actually seen an increased demand for high rejection in satellite communications and also aerospace and defense applications. So this is something that we saw was a growing need that we wanted to satisfy. So what goes into LTCC filter design? So one of the big deals of LTCC material is its high dielectric constant and low loss tangents. And that lets us design in relatively small case styles compared to similar surface mount devices. We are also, in the past few years, we've also gone deeper into distributed filter topologies, and that lets us design at higher frequencies, entering the millimeter wave range, whereas traditional lumped element design suffers at higher frequencies due to the self-resonating frequencies of inductors. So now to talk a little about the high rejection. What goes into allowing these filters to be high rejection? And the big deal is the conformally coded case style, or conformally plated case style. So if you look at the bottom here, on the bottom left, the BFHK is fully plated on all sides, right? And this differentiates itself from our legacy designs, which, if you can see in the center, usually employ these wraparound RF pads, right? So everything has a time and a place, and the wraparound pads are not necessarily bad per se, right? But you do start to see weaknesses in this case style when you start entering the millimeter waves, and that manifests itself in two ways. One is these wraparound case styles can be difficult to tune for return losses, specifically getting that 50 ohm match that you need. And if you see on the right side, we have this what we call the LGA case style. These have their RF pads just purely on the bottom of the component. These typically are what we use for millimeter waves. Another weakness of the wraparound case style is that there's practically no shielding around this sort of case style. So you typically have EM waves sort of radiating out of every single side of this component. And more particularly on the top, if you have any sort of nearby component, you'll notice coupling and interference between these LTCC components and adjacent LTCC components. This is typically as you go up higher in frequency. So on the right side, the LGA case style, this is an improvement for higher frequency performance. You have sort of the top that's plated and you have the bottom that's plated, but you still have the sides open where there can be some EM leakage essentially. That is all fixed with the new BFHK conformally plated case style, where sort of the only openings for the RF signal to leak are in that sort of ring around the RF pads. And if soldered properly to a board, there is virtually no leakage. Okay, so I've talked about some of the great things about the BFHK series of filters. It's great rejection, up to 80 dB. And this is without needing any expensive channelization of your system. I've had customers mention that, in order to achieve such rejections, they might need to put some kind of metal covering around their system in order to help isolate lines or isolate components. And the conformal plating also prevents interference from unit to unit. So what are the downsides? Well, because it has such a specific coaxial-like pad structure, it requires a similar mating to the board that you're mounting this onto, right? And actually, what we recommend for our customers is that they use a board that has a stripline trace, right? That sort of comes up and enters the unit from below, right? So being stripline in nature, this naturally requires a multi-layer PCB, whereas traditionally for our filters, you can mount this onto coplanar waveguide or microstrip, and essentially boards that have the trace on the top layer. So here's just an example of what I'm talking about when it comes to what we recommend as the recommended layout, right? And we give full support for the recommended layouts. Our applications department is fully equipped with being able to help our customers determine what's the best layout and help realize their board stack up. For this example, I'm showing that we're using a 3-layer Megtron stack up, and that's essentially what we use exactly for our evaluation boards. So now, in terms of the actual implementation of this, we do recognize that some customers might not be able to design for such a board. A multi-layer stack-up can be quite expensive, and if they have other components in their systems that are not entirely compatible with such a board, we actually do offer an alternative. So now I want to talk about a subset of the BFHK series, which is the BFHKI-series. And what we've done here is we've taken our BFHK device and mounted it on an interposer board. It's essentially a small PCB. And this sort of solves the interfacing issue of matching the device to the board for our customers. So if you look at the bottom side of the BFHKI filter, it's no longer a coaxial-like RF pad. This can now be mounted on your typical microstrip or coplanar waveguide PCBs. So the BFHKI is great. It's compatible with CPW. It's compatible with microstrip PCBs. It has that same level of conformal coating around to prevent interference from nearby components, and it's only slightly larger than the BFHK. So what are the cons? The cons are that you're essentially now, if you mount this onto a CPW microstrip platform, you are essentially killing the ultra high rejection. The rejection suddenly becomes comparable to any typical LTCC filter in our product line. In addition, due to the additional assembly step, this is more costly than the BFHK. So you might be wondering now, what the heck, why would I buy this BFHKI over a BFHK? And I'm essentially just showing that, yes, this is compatible with CPW. Okay. What I haven't mentioned yet is that the BFHKI device is still compatible with stripline PCBs, the same stack up that I showed previously for the BFHK. So it is still possible to get ultra high rejections off of this device. So when it comes to rejection, right? Rejection in a system is always limited by the weakest link in the system, right? And in the case of the BFHK and BFHKI, it's not the LTCC component that's the weak link. It is the board, right? So with a CPW or microstrip board, where you have the traces on the top layer, you have the risk of coupling between trace to trace, right? And when you're working with rejections, around, I want to say 50 to 60 dB, that's not too much of a concern, right? But when you want to go deep into the rejection territories, 80 plus dB, suddenly that line-to-line coupling does become a big issue, and you need to employ some kind of stripline, PCB, stripline system where the traces are embedded in the substrate. So here I'm essentially showing in the graph performance of our BFHK 8501 compared to the same to the same BFHKI 8501. Same LTCC, just one mounted on a interposer board, one not. And we're able to achieve greater than 80 dB rejection in both cases when mounted on a stripline coaxial launch-like PCB. Now, what I haven't shown in this graph is that actually, as you go higher in frequency, and I'm talking greater than 40 gigahertz range stopband rejection, you'll start to see that the rejection starts to degrade with the BFHKI. The BFHK does maintain rejections at greater than 80 dB for even our high rejection models, but the BFHK does not. And that is because there is still an opening in the interposer where EM signals can leak, right? And that's that opening in the ground around the RF pad that doesn't exist for the BFHK, right? BFHK is pseudo-coaxial, BFHK-I is not. So one solution that we actually implemented for one of our customers is to recommend applying a silver epoxy to the BFHKI. And this can be done using traditional epoxy dispensing methods. And what this epoxy does on the stripline board is that actually closes the gap in that BFHKI, right? And we're seeing that with this additional assembly step, you can actually take a BFHKI and achieve similar ultra high rejection performances as the base BFHK, right? So in conclusion, our BFHK series, it's a series of surface mountable ultra high rejection LTCC filters. They have a relatively small footprint and small cost compared to competitors of similar performance. but it's limited to a stripline PCB if you want to achieve those ultra-high rejections. The BFHKI shares many of the same benefits of the BFHK series, right? But comes with flexibility in mounting. So if you know exactly what your application is, let's say you're deep into test and measurement, you know you need that 80 plus dB rejection, there's no reason not to go with the BFHK series, right? But if your applications aren't set in stone, maybe you're interested in the bandwidth of one of the BFHK series, but you're not so free to design a stripline PCB stack up, the BFHKI serves as a potential alternative, right? And if you do happen to need that ultra-high rejection, it can still be achieved through a similar stripline stack up as the BFHK. So this flexibility in mounting gives the BFHKI its place in our catalog. And that concludes my presentation. It's a relatively quick one.
Thank you very much, William. Any questions? Or are you all keen to get off home? I think it's been a long day, but a very satisfying one. No questions? Oh,
Yes.
How long does the rejections of bands is?
In terms of frequency,
Yeah.
it goes roughly 2.5 times the center frequency for all of our BFHK models.
Okay. So it's a frequency dependent.
It is, yes. So these filters are all distributed designs. So they, the bandwidth, or sorry, the rejection typically would extend 2 times that, the 1 octave higher. But there are additional, design decisions you can make to extend that. In the end, you're playing a bit of game of trade-offs with what you're willing to accept, right? These things tend to increase loss, for example, the more sections you add to a filter.
okay, thank you very much.